We now know that we have access to all wavelengths of the electromagnetic spectrum. We kind of know how to split them in terms of energies. And also, we are becoming aware, hopefully, that not all wavelengths or frequencies will be accessible from the ground. Sometimes we do need to place telescopes in space to observe things like X-rays or the far infrared. What we will be covering now is how to interpret such radiation. And for the full section 5, these are the three main things that we're going to cover. And for this first part of section 5, we'll be focusing on continuum radiation and specifically on black bodies. And I assume that this will be mostly a recap because you should have covered black bodies already. If you don't remember, that is okay. We're still going to go through some of the important properties before we start applying it to, for example, stars. Before I convince you why blackbody radiation is such a major astrophysics tool, it is important to cover some of the important aspects of black bodies. We know that all objects actually they emit radiation with a continuous spectrum of wavelengths. But most objects actually they also scatter or reflect the light incident on them. In a way, a black body or a perfect black body is something that only collects or absorbs radiation but does not scatter or reflect it. Instead, what it does is once it reaches some thermal equilibrium, the radiation that we can see from a black body depends only on temperature. And we can see here a few curves of black bodies going from 8,000 Kelvin down to 5,000 Kelvin. And we'll explore essentially how these curves depend on temperature, where the peak is shifting to shorter wavelengths, but also the integral of this curve is going up significantly with temperature, as we'll see with t to the power of 4. Now, for a perfect black body, such as the one that's behind me, the shape of the curve is entirely determined just by temperature. And in terms of units and what this thing is actually telling you, typically the y-axis will be given in some sort of surface brightness. So what is this surface brightness? Essentially, it is power per unit area per unit wavelength per steradian. So if you want to connect it with what we've covered, this is essentially flux density per steradian of essentially the black body that's emitting the radiation. And sometimes because we measure angles on the sky in terms of arcseconds, it may be per arcsecond squared, but if that is the case, I will definitely point it out. Now, as we can see here, the hotter the black body, then the more the peak shifts into shorter wavelengths. You've of course covered and you've talked about Wien's law, but you also had physics 101, functions and differentiation, where you learned or recapped how to find stationary points. So Wien's law is really just about taking Planck function and differentiating it in respect to lambda, setting it to 0, and then finding all the stationary points. There is only one, and that stationary point that you can see here for 8,000 Armstrong, and then moving to longer wavelengths for colder temperatures is essentially given by Wien's law. So if we do this, this is what we're doing here, is differentiating it in respect to lambda, setting it to 0, and then we find the stationary points or the solution to that equation. There's only one. This is the actual solution. And if you plug in Planck's constant, speed of light, Boltzmann constant, and the temperature, you will get Wien's law, which you can see it in this form around here. You will not need to differentiate Planck's function and get to Wien's law. You can just use it, but I just wanted to recap how you would get to it if you wanted to. So Wien's law is incredibly simple, and it essentially tells you this, that hotter objects have a bluer peak and that colder sources have a redder peak. In other words, if we find a peak of something that's radiating like a black body, we are able to estimate its temperature, and that's incredibly powerful. Now we can very easily write something like a Python script, like I did. You also find this in the lecture notes. If you have Wien's law and you start plugging in wavelengths from the shortest to the longest, you'll start with gamma rays, which are typically defined up to something like 0.01 Armstrong, to then the X-rays, moving on to the UV, to the optical, infrared, microwaves, and also the radio. And this is how I would define it very explicitly between what is radio, microwaves, infrared, optical, UV, X-rays, and gamma rays. One thing that we can ask is, what is the significance of Wien's law in terms of interpreting observations? Well, if you just look at this graph, we can actually very easily deduce that as long as the observations are capturing blackbody emission, then when we're looking at the shortest wavelengths, for example, we're actually looking at gamma rays, and therefore, according to Wien's law, we're actually looking at incredibly high temperatures. If instead we're studying phenomena in the X-rays, we're still looking at very high temperatures of a few 100,000 Kelvin, while in the optical, we're mostly targeting something like 1,000 to 10,000 Kelvin. And it also means that when we move to the infrared and the microwaves, you're looking at some of the coldest temperatures in the universe. So you're going into the Kelvin regime. And this is a very important thing to put things into context. And the reason why, if we want to get a full overview of what's going on in a specific astrophysical system, we do want to look at things at the coldest temperatures and at the highest temperatures. And therefore, we do need access to all wavelengths. In the lecture notes, you will find some examples of how to apply this directly, so you start building up intuition if you don't have it. For example, if we are observing, say, a supermassive black hole in the X-rays, and that is very bright, this emission typically is telling you about something that's happening with temperatures from about 1 million to 1 billion Kelvin, if we just use Wien's law. On the other hand, we actually already use what is the peak wavelength at which we emit when we calculated the magnitude of your friend 10 meters away in section 4. But if we want to do this by using Wien's law, it's relatively simple. We plug in our typical temperature, room temperature of 310 Kelvin, give or take. If you use Wien's law, then you can very easily conclude that our peak emission is in the mid-infrared, that's 9.3 micron. And this is the reason why when you turn off the lights, you won't be able to see anyone in the dark, because we are not sensitive to around 9 to 10 micron. If we were, we would be able to see us shining quite brightly, actually. Finally, another example you have is about some unknown source that peaks at 4,900 Armstrongs. And if you assume that this is a black body, you'll be able to estimate its temperature to be very close to 6,000 Kelvin. And as we'll see, this is something we will be using routinely to actually find temperatures of stars. If we see that a specific star spectrum peaks at, say, 4,900 Armstrong, it is very likely that its surface temperature is very close to 5,914 Kelvin.